All right, students, so now we're going to list everything we know about centroids. So now we're going to be talking about centers of a triangle. We have three centers to be focused on. And the centroid, remember, it is the balancing point, all right? So it's that right there. So if you cut out this triangle from your iPad, that would be the balancing point. That's where you would balance it. Don't cut this iPad out of your this triangle out of your iPad. Don't cut the triangle out of your iPad, because if you do, you will destroy your iPad. I think the librarian will be mad. But anyways, it's found by the intersection of three medians. All right, and then so medians go from angle to midpoint. All right, that's what a median is. So like looking at this one right here, we'll just investigate this one that I'm kind of drawing on right now. This is angle A, it goes to angle A, and it goes to the midpoint. We'll call this lowercase a. That's a median, and it always lies on the inside. Think about it, it's kind of common sense. A balancing point has to be inside the triangle. It can't be on a side or outside the triangle. That's just preposterous to think about. All right, and then centroid lies in the center of the triangle. Centroid, centered. Centroid's one of my favorite words we learn all year. Centroid. Sounds like a robot saying it. Next, we got incenters. List everything we know about incenters. They're found by the intersection of three perpendicular bisectors. Excuse me, timeout. Brain fart, angle bisectors. I don't know why, but I almost had a massive brain fart. Angle bisectors. All right, so right here is an angle bisector, and in fact, I'm going to extend it just for fun. That's an angle bisector. All right, and then that's an angle bisector. All right, boom, right there. All right, and it inscribes the triangle. This circle is the largest circle you can draw inside of a triangle. All right. The largest circle to exist inside triangle. All right, and just how centroid's always in the center, we can think about the incenter always being inside. All right, it's just a fact. It doesn't matter if it's cute, obtuse, right? It's always inside, and it's equidistant to like point I. This is the incenter. All these right here, these are radiuses. It even says that it's a radius. All right, all these radiuses touch the sides, is equidistant to all the sides of a triangle. That's what's so great about it. So if you need to be equidistant to like three roads or three sides of a wall, you'd always pick the incenter. All right, that's why you would use that. And then circumcenter. All right. The circumcenter, this is what I was starting to write before I realized I had a brain fart. The circumcenter is the intersection of three perpendicular bisectors. So in this case right here, like these blue lines, I'm only going to focus on one of them. But notice how this is a midpoint, so it bisects the line and it's perpendicular. We call those perpendicular bisectors. In fact, it's marked for all of them. So the circumcenter is the perpendicular bisectors, and it circumscribes the triangle. All right, and we'll elaborate on that right now. Actually, it's equidistant to all the angles or the vertices, however you want to think about it. Equidistant to all angles / vertices, and we can kind of elaborate if we would like. We're like this right here. This point's the circumcenter. That's the radius of the circle. That's the radius of the circle. That's the radius of the circle. All the radiuses are always the same. So it's equidistant to the vertices, and it lies on the, actually lies anywhere. All right, and we'll elaborate. Acute, it's on the inside. Obtuse, it's outside. And right is on the side. Cool beans. Let's just do a couple algebra problems, centers of triangles with algebra, and then we'll finally call it a review, very lengthy review. But we're gonna use the image on the right to solve the following problem. So given the length QV is 6x plus 10. So that length is 6x plus 10. VU is 4x. We need to find the length of QU. So how do we do this? Well, go in great detail. Remember the median, this whole median, this is the whole length. This length from angle to centroid is 2/3 the whole length. From centroid to midpoint, or centroid to midpoint, is 1/3 of the length. All right. So then if you look at 2/3 to 1/3, well, it's just double the distance. It's double the length. So when we're given these two lengths, we just take the smaller length, centroid to midpoint, multiply by 2, and that will equal centroid to angle. So if we can get that far and just say, well, it's going to be 2 times 4x equals 6x plus 10. All right, if we can get this equation, we're in incredibly good shape. We're going to get 8x equals 6x plus 10. Subtract 6x from both sides. 2x equals 10. Divide both sides by 2, and x equals 5. All right, and it says find the length of QU. So this part right here is going to be 4 times 5, which is 20. This part right here should be 40, since it's double the distance, but let's just confirm. Oh, sweet, I got 40. All right, so the whole thing, QU, is 60. All right, we're going to use the same picture. So this time it's giving me QU. It's saying the whole thing is 30. It's saying QV is 2x plus 2. So this time it gave me, this is the whole length. This is 2/3 the length. All right, so what I can say is I need to multiply QU by 2/3. And this is a nice whole number, so it's not going to be too ugly. But really, this is just going to produce 20. This left-hand side, 2/3 times 30, is going to give me, we'll do some chicken scratch. This gives me 60 divided by 3, which is how I get 20. So 20 equals 2x plus 2. So subtract 2 from both sides. 18 equals 2x. Divide both sides by 2. 9 equals x. All right, so that's some centroid with algebra problems, just some funky things. Just make sure we know the whole centroid's a third, or the whole centroid, that's one whole. That's the whole thing. Centroid to angle is 2/3. Centroid to midpoint is 1/3. Use those ratios and determine the kind of equation you're going to set up. Now we're going to have a perpendicular bisector. All right, so we see some funky stuff with perpendicular bisectors. All right, determine the value of x and y that would force zx to be the perpendicular bisector of yw. So we want this to be the perpendicular bisector. So that means that this is going to have to be the midpoint. So since these notes are already long, I'm just going to focus on the setup. A miracle occurs, and x is 5. So if x is 5, that forces x, this point x, to be the midpoint. All right, so that's one part of the perpendicular bisector. Also, to force it to be perpendicular bisector, point z's on the perpendicular bisector, so it's equidistant to the endpoints of the segment. So with when you have these funky stuff, it looks scary, a lot going on. Really just set things equal to each other, and you should start to become in good shape. Again, not focusing on the solving aspect, because we've already done a lot of math. So that's perpendicular bisector stuff. This one's an angle bisector. So remember, we have an angle bisector right here. Point D lies on the angle bisector. Thus, we have the theorem where D is equidistant to the sides. And this is when we're using like in-center, above the perpendicular bisector being equidistant to the angle, or this is really setting up circumcenter stuff. That's why we use it. It's like the setup for circumcenters. Down here is the setup for the end-center stuff. But nonetheless, we have 3x minus 8 equals 2x plus 2, x equals 10. All right, lengthy review, very thorough. Hopefully you're in good shape so you can experience a lot of success on the test. Good luck. May